topic of strangeness. We're going to talk about our fifth conservation law, but strangeness is the one, well, as the name suggests, which is a bit odd. And so I thought it'd be a good idea just to introduce strangeness as a concept because we've not formally covered that. Okay. Now, we have heard of the strange quark, and it turns out that there is another fundamental number, okay, which is associated with the strange quarks. Now, strange quark has got a strangeness of -1. Okay, so you can already see that strangeness is a bit weird, all right? Whereas previously, for example, our baryons we defined with positive numbers. Our strange quark has a strangeness of -1, and a strange anti-quark is a strangeness of +1. So you can sort of see here why we call this property, whatever it is, strangeness, because it behaves a little bit differently to other ones. Anti-quarks are positive here, and quarks are negative here, and it's usually the opposite way around. Okay. This quantity of strangeness is linked to the time taken for decay. And again, another reason why it is strange is for the following. Okay, strangeness is not always conserved. So when I call the strangeness a conservation law, we have to sort of take that with a pinch of salt. If the strangeness is conserved, then what we find is that the decay has occurred very quickly. Okay, or the interaction has occurred really, really quickly. If it's not conserved, then decay is relatively slow. Okay, we're not talking years here, but it will mean a greater time period. Okay, so there is a rule for this conservation, and that's what we need to look at here. Okay, the strangeness in an interaction, in a decay, can only change by a maximum of 1. Okay, and as I've put at the bottom there, if it changes by 1, then this is a slow process. This could be plus or minus 1. If it's conserved, then it's a fast, and therefore that's due to the strong electromagnetic force. And we'll talk about that at a later date. So in this case, again, our lambda becomes a proton plus an antipion. Let's have a look. Lambda has a strangeness of -1. Proton, 0, and antipion, pi minus, also 0. And so therefore, we've got a -1 becoming 0. Now you can see here that strangeness definitely isn't conserved here, but we've got a change of 1. Our strangeness has increased by 1, and so therefore this is going to be a slow interaction, a weak interaction. Okay, for now, just be happy with the fact that the strangeness can change, but it's only possible for that strangeness to change by 1. Let's look at the other example. Well, I've shown it all on the screen here because it's a little bit boring, okay? In this case, our strangeness is equal, the strangeness of the parent is equal to the strangeness of the daughters. In this case, it must be the case because this is what's called the strong interaction, and therefore it's a very fast decay. You've got 0 becoming 0 plus 0 plus 0. Okay, all these things, the proton, the electron, antineutrino, and the neutron, all have strangeness 0, and therefore the strangeness is conserved in this case. Okay, so just be careful with strangeness. I'm just going to kind of go back to the original slide here. Okay, strangeness can be conserved and strangeness cannot be conserved. If it is conserved, the decay is fast, and if it is not conserved, then the decay is a slow process.